This video is about wheelchair made by Group 20. These members of Group 20. The content of the videos.
So a wheelchair is a medical device designed to assist individuals with leg injuries or mobility impairments, which enable them to move independently based on their needs. In our experiment, we focus on a specific type of wheelchair equipped with a handle that allows movement forward and backward by applying force on it. This type of wheelchair demonstrates key principles of dynamics as its motion responds to both environmental factors and applied forces. And so, to analyze the dynamic behavior of this wheelchair, we will explore four main areas of motion, which the first, kinetic of straight and curve motion, second, advanced motion analysis and vectors, third, work, energy, power, and efficiency, and last but not least, mechanism of system modeling. By applying these concepts, we aim to understand various aspects of the wheelchair's motion, such as displacement, time, acceleration, and also final velocity when force or work is applied on it.
Good morning, Dr. Chan. My name is Lim Hao Leong and my metric number is 24006105105/1. Now I'm going to present about the methodology with the first title, which is Kinematics of Straight and Curve Motion. There are three topics covered in this title, which are rectilinear kinematics for continuous motion, rectilinear kinematics for erratic motion, and also the curvilinear motion with general and rectangular components. To simplify it, the rectilinear kinematics for continuous motion describes the straight line movement of an object, which is wheelchair in this case, using position, velocity, and acceleration over time. Secondly, the rectilinear kinematics for erratic motion describe the irregular or non-uniform straight line movement of an object with changing velocity and acceleration over time. Lastly, for the curvilinear motion with general and rectangular components, it describes an object movement along a curved path using horizontal x and vertical y components of position, velocity, and acceleration.
Now we move on to advanced motion analysis and vectors. To evaluate the wheelchair from that perspective, we apply the concepts of curvilinear motion in terms of normal and tangential components and also vector analysis. So in curvilinear motion, the user will be propelling the wheelchair forward at a constant speed using the handle attached to point P as shown in the picture. So at the tangential component, the formula for the acceleration will be dv over dt. As for the normal component, the formula will be an equals to v squared over rho, where rho is the radius of curvature. So at sharper bands, the rho will be smaller, making the acceleration larger. As for vector analysis, the user will be applying a constant force at the handle, and the velocity and acceleration vectors at point P can be calculated. The velocity of point P will always be tangent to the coupler curve, and the acceleration can be broken down into tangential and normal components, where the magnitude of the resultant acceleration vector equals to an squared plus at squared.
Hello, Dr. Chan. My name is Tan Jack Zhi, matrix number 2400613A/1. I'll now begin presenting the methodology section of analysis of work, energy, power, and efficiency in wheelchair systems. The relevant equations of each scenarios are displayed on the slide. For the first aspect, the work of a force and the principle of work and energy, we design a scenario where a wheelchair with a dummy starts from rest and is pushed over a flat surface by constant force. In the second scenario, which covers conservative forces and energy conservation, a manual wheelchair descends a ramp under gravity to observe energy conversion and potential losses. Finally, for the power and efficiency aspect, we evaluate a user manually propelling a wheelchair across level ground to compare the mechanical input and output during acceleration.
Hi, Doctor. My name is Alvin Chandraliang, and here is our kinematic diagram for the wheelchair that we have drawn. So in this diagram, we have a total of 4 links and 4 primary joints, as the joints are only connected with simple links, which causes them to be only primary joints but not complex joints. The 4 bar mechanisms occur at the location of the main wheel with the handle, where when the user turns the handle, the 4 bar mechanism will occur where it will also turn the main wheel, which causes the whole movement of the bar. Besides that, for the slider mechanism, we have chosen the folding frame as our slide, where it is located behind the main wheel of the wheelchair. We choose that part as our slide as we believe that it could help us reduce the size of the wheelchair by sliding it.
In this study, we make assumption of the scenario for the calculation of our topics. For rectilinear kinematics for continuous motion, the wheelchair starts from rest with 0 initial velocity and accelerate uniformly with acceleration 0.5 on a flat, smooth surface in 4 seconds. And we got the result with final velocity 2 meter per second, displacement 4 meter, and alternate final velocity v equal to 2 meter per second. For the curvilinear motion with general and reticular components, the scenario we made is the wheelchair rolls down a curved slope defined by the equation y equal to 0.08 s squared, and given that the x at 7 meter, the horizontal velocity is equal to negative 2 meter per second, and the horizontal acceleration x is equal to minus 1.0 meter per second squared. Then we got the result with velocity component is equal to negative 2.24 meter per second, and the acceleration component, which is negative 0.672 meter per second squared. For the rectilinear kinematics for erratic motion, the wheelchair travels over an uneven surface where its velocity changes irregularly over the time. And for this, we made a simulated sample velocity time theta, and we also made a graph to represent the data we made. Then we use the trapezoidal rule to calculate the approximate displacement, and we get the displacement is equal to 4.5 meters.
Next is the results for advanced motion analysis and vectors. For curvilinear motion, we assume the user's hand moves at a speed of 1.2 meter per second along the path. So for the tangential acceleration, we estimate it to be 0.5 meter per second square. For normal acceleration, using the formula an equals to v square over rho at the widest curve where rho equals to 0.6 meters, the acceleration will be 2.4 meter per second square. Whereas at the tightest curve where rho equals to 0.3 meters, the acceleration will be 4.8 meter per second square. Using the accelerations, we can calculate the force as well. So for the tangential force, for one arm is 22.5 newtons, whereas for the normal force, we have minimum and maximum curvatures. So for minimum curvatures, we have 108 newtons per arm, and for maximum curvatures, we have 216 per arm. Whereas for vector analysis, the hand's velocity vector will always be tangent to the curve, and acceleration vector split into tangential and normal components. So we need to calculate the resultant acceleration vector. So at the sharpest curve, we take the maximum acceleration, which is 4.8 meter per second square, and calculate the resultant, which gives us 4.83 meter per second square. As for the flattest curve, we take the minimum acceleration, which is 2.4 meters per second square, and calculate the resultant, which gives us 2.45 meters per second square.
For the results of the work of a force, the principle of work and energy and the systems of particles, the assumption used in the calculation along with the free body diagram are shown on the slide. In case A, where no resistance is applied, the final velocity of the wheelchair is calculated to be 3.33 meters per second. In case B, with a rolling resistance of 20 newtons, the final velocity is reduced to 2.98 meters per second. By comparing the two cases, we can see that rolling resistance causes a noticeable reduction in speed, demonstrating the impact of resistive forces on wheelchair motion and energy efficiency. Next, we examine the scenario involving conservative forces and energy conservation. The relevant assumptions and the free body diagram are shown on the slide. In case A, where the ramp is frictionless, the final velocity at the bottom is calculated to be 5.43 meters per second, and the time taken to reach the bottom is 2.21 seconds. In case B, with a 20 Newton rolling resistance, the final velocity decreases to 5.17 meters per second, and the time taken increases to 2.32 seconds. This shows even moderate resistance results in slower speed and longer travel times, emphasizing the importance of accounting for energy losses in real-world wheelchair motion. For power and efficiency, the relevant constants and the free body diagrams are shown on the slide. Based on the values used, the input power, which is the total power exerted by the user, was calculated as 76 watts, while the output power, representing the rate of kinetic energy gain, was 36 watts. This gives us a system efficiency of approximately 47.4%, meaning that just under half of the user's effort goes into actually moving the wheelchair. The remaining energy is lost due to rolling resistance and other factors.
For the results from the kinematic diagram, we can calculate the degree of freedom of the wheelchair. So the calculation of the degree of freedom can be done by the Gruber's equation, where the formula is m equal to n times n minus 1, minus with 2 times with the primary of joints, and minus with the number of complex of joint, where our length is 4, primary joints are also 4, and the complex joints are equal 0, where the results will be 1, which shows that our wheelchair will have only 1 degree of freedom.
Next, we proceed to a discussion. The rectilinear kinematics with uniform acceleration in this study refers to the analysis of a wheelchair moving along a straight line with constant acceleration. In this context, the velocity of the wheelchair changes at a steady rate over the time. And this allows its motion to be described using the simple kinematic equations. So this type of analysis from the calculation is very crucial and essential in the early stage mobility evaluation. This is because it provides a baseline data without the complexity of different forces or curve path. It helps in understanding how the wheelchair could behave in ideal control environments such as smooth corridors or ramps, where the performance can be optimized or comfort and energy efficiency. Moving on to the rectilinear kinematics with erratic motion, it refers to the analysis of a wheelchair moving along a straight line but with changing velocity or acceleration. Unlike continuous motion, where the wheelchair accelerates uniformly, erratic motion involves variable and different forces that are probably caused by the obstacle, uneven terrain, or the resistant forces. The use of the graphical analysis and numerical methods like the differentiation or integration are important in analysis of erratic motion. This is because in real-world scenarios, the forces and the speeds are not consistent as the scenarios stated in the simulation. This approach gives a realistic insight into the performance, safety, energy demands for the wheelchair in real-world applications. Last but not least, this study also stated that the curvilinear motion refers to the movement of a wheelchair along a curved path, and it broken into x and y components of position, velocity, and acceleration when we analyze using the general and rectangular components. Rather than focusing on the entire curve, we analyze the motion along each axis, which is x and y component independently. This also makes it easier to compute the changes in speed and direction. This analysis demonstrates how the wheelchair curve path affects both direction and magnitude of its motion, which is very crucial for understanding stability, safety, and control during the navigation over a slope or curved terrain.
Moving on to advanced motion analysis and vectors. So for curvilinear motion, the tangential component corresponds to changes in the speed of the hand along the propulsion path. So the user generates moderate tangential acceleration. This reflects the direct effort used to accelerate the wheelchair forward. The normal component will arise due to constant changes in direction along the curved path. So when the hand speed remains constant, directional changes still occur that results in centripetal acceleration. So this results in significant normal forces which can contribute to joint and muscle loading. As for vector analysis of motion and forces, the motion at any point of the propulsion path can be represented as a combination of tangential and normal vectors. So the velocity vector is always tangential to the X-shaped path, while the acceleration vector is the resultant of the tangential and normal components. This confirms the presence of dynamic variability throughout the propulsion cycle.
For the work of a force, the principle of work and energy and systems of particles, based on the calculation, the final speed drops to 2.98 meter per second from an ideal 3.33 meter per second when a 20 Newton rolling resistance is introduced. This represents a 10.5% reduction in speed. This means manual wheelchair users must exert significantly greater force to overcome friction, increasing upper limb strain, fatigue, and the risk of long-term shoulder injuries. This underscores the importance of optimizing motor torque and energy efficiency during wheelchair design, reducing mechanical resistance through better wheels and bearings, and improving rolling surfaces in public facilities to minimize user effort and power demand. Next, for conservative forces, the speed decreased by approximately 5% when 20 Newton of rolling resistance was introduced. This means 120 joules of energy was consumed to overcome resistance. This result shows that ramp design should minimize unnecessary resistance to ensure a safe and controlled descent for assistive devices like wheelchairs. For manual users, it requires more physical efforts, raising the risk of fatigue or upper limb injuries, especially during frequent slope navigation. Next, for power and efficiency, we found the efficiency to be around 47.4%. This means that just under half of the user's effort is converted into useful forward motion. The remaining 52.6% is lost to rolling resistance. This relatively low efficiency highlights the energy cost of overcoming friction even on flat terrain. Over longer distance or uneven surfaces, the effort needed increases noticeably. As a result, manual wheelchair users may experience fatigue more quickly, especially during repeated propulsion or acceleration. To improve efficiency, we suggest reducing rolling resistance by using high-quality tires, better bearings, or optimized frame weight. Assisted push systems or kinetic energy recovery may also help reduce energy loss.
For the discussion of the mechanism and system modeling, we will first discuss the degree of freedom. And for the results of the degree of freedom, which we get one, we can indicate that the wheelchair is not fully fixed and it has the capability of movement where we will be able to move the wheelchair by applying force towards the point of interest, which could let it move forwards and backwards. For the slider mechanism, we choose the folding frame as it will slide during the folding of the wheelchair, which causes the wheelchair to be easily stored or transported.
Up next, we have our limitations and improvements of our study. First of all, we have limited real-world validation because the study is largely theoretical and lacks experimental data. So how to improve it? We can add motion capture systems that validates theoretical predictions with also experimental evidence. Secondly, we have idealized assumptions. All our links are assumed to be rigid, frictionless, and perfectly planar. This ignores the real-world factors like joint backlash and also link flexibility. So improvements like conducting a full mechanical energy audit can be done to allow meaningful comparisons. Third, we have lack of user customization for the wheelchair. The 4-bar linkage mechanism has a fixed design and does not account for individual differences. So improvements like introducing an adjustable linkage that accommodates the different preferences could be done.
Valuable learning experience for all of us. Through collaboration, research, and analysis, our team was able to explore real-world challenges and propose practical solutions. We have gained not only technical knowledge, but also a deeper appreciation for teamwork and problem solving. This experience has strengthened our ability to work together and has prepared us for future engineering projects and innovation.